Thank you. So you guys can hear me okay. So quick conflict of interest slide. So per Jason's introduction yesterday as the token medical physicist, my role in this course, I think, is to mainly give you a bunch of definitions for things that you're going to hear the rest of the time. So this is a pretty basic talk that's going to cover some basic physics as they apply to radiosurgery, a lot of definitions, a little introduction to treatment planning, and then at the end, a little dose uncertainty. And so I'm going to split the talk into those same four pieces, basically. So we'll just get right to it. So we'll start at the very beginning. What's this radiation stuff that we deal with radiosurgery? So radiation is any process in which energy is emitted and propagated through space. It can be in the form of particles or electromagnetic radiation, and here you see on the slide, you can see this is an alternating set of electric and magnetic fields, which is kind of electromagnetic radiation, but you can also have particles, and in quantum mechanics, there's the theory that particles have properties of waves and waves have property of particles. But in general, we sort of talk about, gamma rays and X-rays for radiosurgery and charged particles, which are usually protons. When you're talking about radiation, there's a bunch of units and measurements to describe radiation that you need to understand. And a lot of you in the audience probably already know these, but for those that haven't had a lot of radiation training, we'll just really quick go through them. So there's the notion of energy, which is in units of joules, activity, which is, if you have radioactive material, it's kind of how active it is. So how many disintegrations per unit time, which is in units of curies or becquerels. There's exposure, which is how much ionization the radiation is causing in Roentgens or coulombs. Absorbed dose, which is the one you're most interested in and probably most familiar with, which is these days usually in units of Gray, and then biological dose equivalent. But because it's pretty early in the morning and I'm just the token physicist, just forget all this for the moment and just remember it this way. So becquerels, how active, this is activity. How brightly does your radioactive material glow? Gray, how brightly will it make you glow? So how much dose are you absorbing? And sieverts, what does it do to you in the end? How many extra eyes do you have? Just, if you're going to use this definition, just remember that when you're dealing with photons and particles, they're not in general going to make you radioactive. It's just how much dose are you absorbing. So a unit that you're going to hear probably a little bit in this course and a lot if you're in practice with radiosurgery is the notion of photon and particle energy, and it's in units of electron volts and usually mega electron volts. This is just the amount of energy carried by each photon or each particle. Here are the equations for both of them. I'm not really going to go through exactly what the equations mean or where they came from. But just remember that the higher the energy in general, the deeper the penetration if it's a photon. And so example terminology you'll hear is like a 6 MeV photon or a 150 or 200 or 250 MeV proton. So now you know where that comes from. There's a couple different sources, like I mentioned, for radiation that we use in radiosurgery. The first one is using radioactive material, and the classic example of that is cobalt-60, which is used in the Gamma knife. And so cobalt-60 gets created from cobalt-59 in a reactor through neutron bombardment. It becomes cobalt-60, but cobalt-60 is neutron heavy, so it wants to convert a neutron into a proton. And in the process, it releases a beta particle, which is an electron, and an antineutrino, and it becomes nickel-60. And it becomes nickel-60 at an elevated energy state, so when it drops to its base energy state, it releases 2 gamma rays of 2 different energies. And this is what we actually use to treat patients. This little electron gets absorbed inside the sources of the Gamma knife or whatever device it is, so it doesn't really have much to do with treating the patient, and the antineutrino doesn't really interact, so it kind of just wanders away. And whenever you have a decaying radioactive material, its activity is going to decay by the relatively well-known decay equation, and the activity is in units of becquerels or curies, like I mentioned before. So again, cobalt-60 is what runs the Gamma knife. So just to describe a Gamma knife in like 30 seconds, you have 192 cobalt-60 sources that are sort of here and here, but this is a kind of like a styrofoam coffee cup shaped collimator system. So they go all the way around, kind of in a cylinder. They're in 192 sources split into 8 sectors that are driven by motors in the back of the unit so that you can move the sources over these beam channels that you can kind of see in here. And then there's some shielding doors and a positioning system that moves the patient so that the target of interest is at the focus of all the beams. So that's how a Gamma knife works, pretty simple. So if we're not using radioactive material, then the way we do things is by making our own X-rays. And the way that works is we bombard a high atomic number target with electrons. And here you can see some electrons coming in. And depending on how they interact with the nucleus of the atom, you get different kinds of interactions. But in general, what happens is the electrons decelerate and they change direction. And when that happens, you get X-ray emission. So that's basically how we make the X-rays. That's called Bremsstrahlung. Physicists love using that word, I think, just because it's a big German word. So the classic way you use this is with a linear accelerator. Let's see if that stops in a sec. All right, there we go. So here's a linear accelerator in probably 120 seconds, because it's a little more complicated than a Gamma knife. So the simplest linear accelerator you can think of would be this, where you have a filament, and when you heat it up, it releases a cloud of electrons. And on the other side, you can put a tungsten target. And if you put an enormous 6 million volt battery between them, then this side's negative, this side's positive, so the electrons want to go from negative to positive. So they accelerate across the space, and when they hit this target through Bremsstrahlung, you get X-ray production, and so you get X-rays back out. A real linear accelerator is obviously more complicated, and here's a quick schematic. And just to take you through it, you have a pulse modulator, which is the best way to think of it is kind of like a timing unit that creates a timing signal that gets sent to an electron gun and a microwave power source. When the timing circuit gets to the electron gun, the electrons release some electrons into this waveguide that I'll talk about in a minute. And at the same time, the microwave power source creates microwaves that get sent to the waveguide. And then in the waveguide, the two interact to accelerate the electrons across the waveguide to very high speed. Then they go around a magnet to bend them towards the patient. And then they go through the treatment head of the linear accelerator. And I'll describe that in a minute. And then they get to the patient. So just to briefly focus on the waveguide for a second, the way it works is a waveguide is basically a tube with different sized cavities cut in it, and the frequency of the microwave radiation that's coming in causes resonance within the cavity and basically causes alternating positive and negative charges on the walls of each cavity. And so if you have an electron bunch that comes in at the same time as the waveguide, then you can make the electrons basically surf along the cavity. So it kind of looks like this. So that's basically what happens. So to back it up, just whenever, in this cavity, the electric field's negative, so it accelerates the electrons, and then at the same time they get to the next cavity, it's still negative, so it just surfs along. So now we have electrons that are moving at high speed. They get into the treatment head of the magnet, of the LINAC, which is down here. And here's a cutaway of how that works. So you have an electron beam. It impacts a target, creates X-rays through Bremsstrahlung interactions mainly. They get collimated by a primary collimator, and they become a forward-peaked beam, which then hits a conical flattening filter, which flattens out the beam like this. And then in the meantime, it goes through a secondary collimator and then something called a multi-leaf collimator that I'll talk about in a minute so that you can shape the beam and then it gets to the patient. So that's basically how a LINAC works. For radiosurgery, you can shape the beam 2 major ways. One is through radiosurgery cones, which is a tiny little cone you put on the bottom of the LINAC that creates circular fields. Or you can use multi-leaf collimators, which are like little leaves of tungsten usually, that can modulate and shape the field into more complex shapes, and even in this case, little island shapes if you're treating more than one target. So one thing when I was training that was always really confusing is, I just described that photons have energies that are described in units of MeV, But a lot of times you'll hear somebody say, I have a 6 MV Linac. And there are a lot of questions when you're training that you're always too afraid to ask. And this was always, for me at least in the beginning, one of them. So one thing that's important to remember, to back up a minute, is that when the electrons hit an X-ray target and they have Bremsstrahlung interactions, the photons that get created are all different sorts of energies. So you get an actual spectrum of energy out of the Linac. And so that's why they started naming them in units of MV, not MeV. So a 6 MV Linac has a maximum potential energy of 6 MeV photons, but in fact, the mean photon energy is about 1/3 of that, and you can kind of see that here, where here's the 6 MeV curve, or the 6 MV curve, and the mean is somewhere over here. So now we've been through a Linac and a gamma knife, so we have photons that are hitting the patient, whether they're gamma photons or X-ray photons. So how do they interact once they hit the patient? So there's several different modes of interaction that I'm not gonna go through all of them, but the most common one at the energies we're dealing with is Compton scattering. And the way that works is an incoming photon hits a free electron on an atom and it has enough energy to knock it out of its orbital shell, basically ionizing the atom. And it changes the direction of the gamma ray because it's lost some energy, and it knocks the electron out in a different direction. And the electron has high enough energy to go on and ionize more atoms after that. And so it's this ionization that creates free radicals, causes DNA damage, and all the things that our talk yesterday discussed. So what do you mean when you actually give a dose in gray? So to this end, photons are indirectly ionizing. So the photons don't do the work by themselves. They free secondary electrons that go on to cause ionization. That ionization results in absorbed dose to tissues. And so dose is the energy absorbed per unit mass, which is units of gray. And so this is kind of a schematic of that. You have a photon coming in, and then these green lines are all the electron paths. And this is another view of it. Indirect ionization is on this side. You have a high energy photon. It can penetrate into the tissue a ways before it actually has an interaction. But once it has an interaction, you get a whole chain of ionization events that go into tissue. And so the absorbed dose goes all down this way. So if you are trying to model an electron or a photon beam, there's a couple basic principles. One is the principle of attenuation. If you have a point source of radiation in a water tank and you're measuring along the beam, you get a depth dose distribution that looks something like this, where the dose initially builds up to a maximum and then it drops off exponentially. This is actually an important point for all radiation therapy, including radiosurgery, where this portion of the curve is called the buildup region, and that's why you can irradiate somebody with high energy photons without destroying their skin. So it's called the skin sparing effect. And the reason why that happens is because the photons, when they create electrons, they tend to create them downstream. So the interactions all happen at a deeper level than the initial interaction. If you're doing modeling, another thing you need to model is the inverse square law. So if you have a point source of radiation, then the intensity of that falls off with the square of the distance. And the reason for that is that if you have the same number of photons coming out of this source, the number of photons that pass through the ever-expanding patches of surface area as you go farther out drop off by the square. So that's why it falls off by the square of the distance. You also need to model the beam profile. If you have the same point source and a water tank and you scan across instead of along the photon beam, then you get a profile that looks something like this. And then there's a definition of penumbra, which is sort of the beam edge. And that's usually defined as the distance between the 20% of maximum and 80% of maximum dose. So you'll hear that a lot, especially when people are trying to compare machines. They'll talk a lot about, is the penumbra worse or better? So you might hear that. So that's enough for basic physics for the moment. Let's talk about radiosurgery. So how is radiosurgery different from traditional radiation therapy? So here on this side, you see a sort of typical broad field multiple fraction radiation therapy treatment where you have large fields that by definition are irradiating targeted tissue and normal tissue. And so because of that, you try to prescribe a homogeneous dose that you can take advantage of differential biological effect via just differential repair pathways, and you use a low dose per fraction and a high number of fractions to spare normal tissue damage. Radiosurgery, on the other hand, uses really small fields that are tightly conformal to the target, use high doses per fraction with either one or a small number of fractions, and have very steep dose gradients. And because of this, the requirement for precision and accuracy is a lot higher, because if the dose fall off here is upwards of 20% per millimeter and you're off target a millimeter, then you're going to misdose the periphery of the tumor by up to 20%. So it's a big deal for radiosurgery. So one of the basic principles of radiosurgery is spread out the energy. So whether you're using gamma knife, which uses a lot of beams, or cyber knife, which uses a lot of beams aimed at the target, or you're using multiple arcs if you're doing photons on a LINAC, the basic principle is exactly the same, which is you're going to spread the energy out as much as you can, and that's how we generate these tight dose gradients. That principle, spread out the energy, have all the beams aimed at a point, that doesn't do you a lot of good unless you actually know where you're pointing that focus at. So there's a couple techniques for doing this. One is a framed-based technique where the patient has a frame put on their head. The frame has a localizer box, and the localizer box has a pattern that shows up as fiducials on the image, and by knowing where these fiducials are, we know where we are in three-dimensional space, so we know where we're going to point the focus of all those beams. There's also image-guided techniques that can use a frame or not a frame, and they use the onboard imaging capabilities of the machines to help guide where the localization is. So here you see a LINAC with an onboard X-ray system or an onboard CT system. Here's another one that uses orthogonal X-rays, and you can also have optical tracking and surface tracking for during a treatment to make sure you know where the patient is. And then there's other machines that use MV imaging. So there's all sorts of ways to do image-guided techniques. The way those basically work is you have a set of images that you use for treatment planning that are usually done on a CT simulator. You match those to the images you get daily with the imaging system on the machines, and through a co-registration you get a positional error that tells you how far off the patient is from the position you plan them in, basically. And so to be able to treat, you need the patient in the same position every time so it matches the plan. So you'll see that happen a lot. You also want to try to keep the patient still while you're treating them. There's a bunch of different immobilization techniques that you can use for both regular radiation oncology and radiosurgery in particular, and they include, conformal vacuum cushions, frames with bite blocks, thermoplastic mass systems, and approaches that use combinations of all of these, as well as the frames I discussed earlier that are more invasive. So now let's move into radiosurgery treatment planning a little bit. So one basic concept you have to understand before you can understand treatment planning is what we mean when we say an isodose distribution. So when you make a radiosurgery treatment plan, you're basically creating one of these isodose distributions. The best way to think about it maybe is that it's just like a contour map of a mountain where each of these lines is a location of equal dose. And you can see if you draw a profile through this isodose distribution, you get what looks kind of like a mountain. You're going to usually prescribe dose to one of these lines. So if you prescribe dose to this yellow line, which is the 50% line, and you give it 15 gray, that's exactly the same as saying you're going to give 30 gray to the 100% line, or 22.5 gray to the 75% line, or 6 gray to the 20% line. So you're usually going to prescribe some dose as some amount of absorbed dose in gray to some percentage isodose line. So you'll see that all through this course, and obviously when you're reading about doses to different targets in clinical papers. There's two basic approaches to treatment planning. There's forward planning and inverse planning. In forward planning, the person doing the treatment planning kind of manually decides basically everything from beam placement and beam weighting to how they want the shape of the isodose distribution to be, and it's an iterative process to achieve the different planning goals. There's also inverse planning, where the planner, instead of determining the geometry, determines dose constraints, like how much dose should go to how much volume of each target. And then the computer optimizes the plan to try to meet those constraints. And it's also usually an iterative process and requires a bunch of tricks to get the dose shape correct, because here you're dealing with shape and here you're dealing with dose constraints, and you're kind of giving up control of shape. So there's a balance between them. Here's an example of forward planning on a Gamma knife, where you have a tumor that you're trying to treat and you put different spot sizes on it. So the first one obviously is too big, so you keep adding spots one by one, and you weight them until eventually you get, if you add enough of them with the right shapes and the right locations, you get a dose distribution that's tightly conformal to the target. Here's an example of inverse planning, where this one's a little hard to see, but down here you have different dose constraints, like the cord can have a max dose of 4,700 centigrade, right? So you have a list of these constraints, and then the computer will try to go off and find a solution that meets all the constraints. Once we have a treatment plan, we need some way to evaluate how good they are, so you need to understand the concept of a dose volume histogram, and that's just a graph of the relative volume or the absolute volume versus dose. So the volume receiving at least some dose, and here you can see a bunch of different curves, and usually your target, you want to have a curve that's way over here to the right, and your critical structures, you want to have curves way over to the left, meaning they're not getting a lot of dose. And so we use this to evaluate tumor coverage, dose homogeneity, dose to critical structures, all sorts of things. But what's important about this is it ignores the geometry of the dose distribution. So it lets us have a very quantitative answer, but it's not by itself sufficient to evaluate a plan. We also use things like conformity indexes, which we mentioned a little bit last night, but here's some examples. And these sort of try to describe how well the plan matches the target. And the two most popular ones are probably the RTOG index, and especially in radiosurgery, the Paddock conformity index. And that's defined as the volume of the tumor receiving at least the prescription isodose divided by the total volume of the tumor times the volume of the tumor receiving the prescription isodose divided by the total volume of the prescription isodose. So this term is just sort of the fractional amount of the tumor you're treating with the prescription, and this term tells you how much normal tissue you're treating. So you get penalized if either of these don't work out right. And so one is a perfect number, and here on this side, you can see different indices people have come up with, and in different situations, what number you would get. One problem with the RTOG index is that you can actually get a perfect score without actually hitting the target, which is what the Paddock conformity index tries to rectify. So before I leave sort of the treatment planning, physics-y part of the talk, I just want to talk about the terms that get thrown around in radiation oncology. So you're going to hear things like 3D conformal and IMRT and VMAT and IMAT and IGRT and SRS and SRT and SBRT and SABRE. There's like all these terms, and they can get pretty confusing. What's important for radiosurgery is that they actually use all these other things. So radiosurgery can be done using intensity modulated radiation therapy and volumetric modulated arc therapy, and uses image guidance. So try to understand what all these terms are, but just remember that radiosurgery uses a lot of different techniques. So to end the talk, I want to talk a little bit about uncertainty. Radiosurgery is a pretty complicated procedure, right? We've just touched on the very basics. This is a pretty short talk, but there's all sorts of sources of uncertainty, including beam delivery uncertainty, which include things like calibration uncertainty and positioning and mechanics. There's imaging uncertainty, which has to do with how well you can tell what your target is and where it is. There's biological uncertainty that we touched on last night. All of these play into your ultimate treatment uncertainty. And so if your treatment planning computer is displaying some curve that's beautiful and totally covers the tumor, what you're actually delivering is something hopefully not this blurry. This was obviously an exaggeration, but you're not actually delivering the same thing. As an example, this is a slide I got from Stan Benedict at UC Davis, but here you can see, you would expect to have a lot of respiratory motion up here, but what's going on down here with the spinal cord, right? It's not just staying in place. So if your treatment plan is assuming this isn't moving, you might be a little bit surprised. So it's important to keep this in mind. So the last set of definitions I'm going to talk about today is what we usually do about that in radiation oncology. There's a whole set of margins that have been developed that account for different sources of uncertainty. So you might hear people say, I'm going to prescribe some amount of dose to the PTV, which is the planning target volume, or the GTV, which is the gross tumor volume. So that's what these things are. So the gross tumor volumes, the known imaging evident tumor, the clinical target volume expands that to account for uncertainty in tumor extent. There's something called an ITV that accounts for motion, and then there's a PTV which accounts for setup and delivery, and all of these are expansions. So you have a GTV, PTV, CTV, so they get bigger and bigger. But in radiosurgery, these aren't so formal, and in fact, a lot of the time we don't use them. But especially probably for spinal radiosurgery, you'll hear these terms thrown around. The other thing you need to know is that nobody really knows what the right margins should be for radiosurgery, but it's just something to keep in mind because you'll hear about it all the time. So to summarize, radiosurgery and radiation oncology in general is pretty jargon heavy, and they like their acronyms, so try to understand what they are. The details of the physics can be complicated, but as I think you've seen, the general principles aren't really that complicated at all. Don't be afraid of your physicists, so we exist to ask, answer questions, hopefully, or at least try to find the answers, so try to keep us in mind. And remember that what you see isn't exactly what you get when you're treating somebody, so don't just totally trust your computer. That's all I have.